And in the last section, I would like to share some methods of evaluating the results of regression analysis. At the beginning of today's lecture, I told you that to be able to undertake interval estimation and hypothesis testing, the error term or the disturbance term needs to be normally distributed. We've seen the theoretical assumptions behind the normality assumption, and now I would like to show you how to check it practically, right? Which tests to use, which methods to use to prove that the error term is indeed normally distributed. Today I would like to discuss just two methods, but actually there are many more of them. But for this course, you just need to know two of them. So it's histogram of residuals, so we can just make a histogram of residuals, and we can also use the Jarque-Bera test. Let's go through these methods one by one. So histogram of residuals. So what we do is that on the horizontal axis, yes, please have a look at this graph. On the horizontal axis, we divide the values of the residuals, right, the estimated residuals, into suitable intervals. Like in this case, the suitable interval is 0.5. And in each class interval, we erect rectangles equal in height to the number of observations. So if you look at this graph, you will see that the residual in this interval, there are two of them, right? Two residuals. In this interval of negative 1, so I guess from -1 to -0.5, there is one residual like this. From -0.5 to 0, there is one residual like this. From 0 to 0.5, there are four residuals like this, and so on and so forth. So this is how we construct such a graph. And then we say that the residuals are normally distributed if the constructed graph has a bell shape, right? The shape of a normal distribution. If you look at this graph, I don't think it looks like a bell shape. So in case of these residuals, they are not normally distributed, right? Because this graph does not have this bell shape, like a hill shape. So it's quite actually uneven. And the second method, more official one, is the Jarque-Bera test of normality. Here in this slide, you can see the formula. So asymptotically or in large samples, this statistic follows the chi-square distribution with n-k degrees of freedom. The chi-square distribution is another type of distribution. We also discussed it during the class of statistics, and I will share the table with you in my files. So, but for now, just focus on the formula. So to get the statistic, we need n, which is the sample size, the number of observation. We need s, which is skewness coefficient. And for a normally distributed variable, s should be close or equal to 0. And k is kurtosis coefficient. And for a normally distributed variable, k should be close to 3. So if you substitute the value of 0 instead of s and the value of 3 instead of k, actually what we get in the brackets is 0. So we can say that the error term will be normally distributed if the Jarque-Bera statistic is equal to 0 or very close to 0. Another way we can interpret the results is using the p-value. So if the computed p-value is sufficiently low, we reject the null hypothesis that the residuals are normally distributed. And consequently, we accept the alternative hypothesis that actually they are not normally distributed. And if the computed p-value is reasonably high, then we do not reject the null hypothesis and we say that the residuals are normally distributed. So there are two ways that the test result can be interpreted. So if it is close to 0, then we say that the residuals are normally distributed, or if the p-value is very high, then again we say that the residuals are normally distributed. However, if the test is either very different from 0 or the computed p-value is very low, then we say that the residuals are not normally distributed. And on this slide, I just want to quickly explain what skewness and kurtosis mean. Skewness, this is the lack of symmetry. And if you look at this graph, the dotted line, this is the symmetrical case, so this is the normal distribution. And the case of not normal distribution will be this right skewed graph or this left skewed graph, right? And as I told you before, for normal distribution, S skewness coefficient should be equal to 0. As kurtosis, this is the tallness or flatness of the curve. So if the dotted line, this is the case of normal distribution, and it is known as mesokurtic. So if the graph is, if the distribution curve is said to be mesokurtic, then it means that it is normally distributed. However, if it is too tall or it's leptokurtic, then the area term is no longer normally distributed. Or if the curve is too flat, like this platykurtic case, then again the variable is not normally distributed. And as I told you before, k should be equal to 3 if in case of normal distribution.